In this video, we are going to discuss the question paper 4-2 of 9701 Chemistry, the examination series May-June 2025. Now here is question 1, but before we start with question 1, let me explain you one point here is that we can just discuss the answers in the question papers. While discussion of the question papers, we can't explain you the whole theory behind the question answer. Like for example, here it's given describe the trend in the decomposition temperature of group 2 nitrates and explain your answer. Now we can just give you the points to be written here. We can't explain you the whole theory here during the discussion of the paper, because for that either you will have to go through the books, reference books, or you will have to see the other videos where the whole topic is being explained. Because here we are falling short of the time and the whole theory just cannot be explained on the limited space given in the paper. So try to understand, we are just giving you the points which are important to write according to the marks given. That is, for example, here 3 marks a question is given. So for 3 marks, what are the points you need to cover? That only can be explained during the paper. So now let's start with the question 1. Here it says calcium nitrate decomposes on heating. Write an equation for the decomposition of calcium nitrate. Now you need to know what is the formula of calcium nitrate, that is CaNO3 twice is the formula, and we can write that as CaO plus NO2 plus O2. Now there is a simple balancing required here. This is the balancing you will need, or you can just write 1 1 1 and O2 is half. You can do that also, that is 1 1 2 and half for the oxygen. That also can be written. Now describe the trend in the decomposition temperature of group 2 nitrates. Now understand, the decomposition trend and its explanation is same for group 2 nitrates and carbonates. That goes the same, only one term differs, and that I'll explain you during the explanation and the description. So first thing we need to explain here is describe the trend. Now what's the trend? The trend, the decomposition temperature for group 2 nitrates. I'm not writing the decomposition temperature increases down the group, Now what does that mean? That if magnesium nitrate is compared with calcium nitrate or strontium nitrate, then the strontium nitrate will require higher temperature for the decomposition and magnesium nitrate will require lesser temperature for decomposition. That's what is meant by the decomposition temperature increases down the group. Now why that happens is, as the cation size increases, we know down the group the cation size increases. So as cation size increases, the most important point is that the ion polarization decreases with the increase in the cation size. So the ion polarization decreases. Now this happens because as size increases, the attractional force between the cation and anion decreases, and hence the ion is, that is anion is not polarized easily. So ion polarization decreases, and because of that what happens is the NO bond gets stronger. NO bond gets stronger. So if NO bond gets stronger, that is inside the nitrate molecule. If NO covalent bond of NO gets stronger, it's difficult to break it and decompose it. So as NO bond gets stronger, the temperature required to break it also increases, and same thing happens with the carbonates also. What's the difference is that for the whole answer remains same. Here only you have to write the CO bond gets stronger rather than NO, because here we have nitrates in the carbonates, the bond is CO in the carbonates. So that's the only difference when you write about the carbonates, otherwise the whole answer remains the same. Now let's see what's the next part here. It says a sample of 0.33 gram of strontium oxide, that is SRO, is completely dissolved in distilled water to form a solution of strontium hydroxide. The resulting solution is added to a volumetric flask and made up to 250 centimeter cube with distilled water. Calculate the pH of this solution at 298 Kelvin and give your answer to 2 decimal place. Remember, you have to calculate it for 2 decimal place and the pH of the solution is at 298 Kelvin. So the first thing what I'll do is that strontium oxide is having the formula that is dissolved in water. It dissolves in water, actually reacts to form the strontium hydroxide solution. So here you can see the equation is already balanced and we don't need to balance. So the ratio here is 1:1. Now, so the first thing we'll do is that we'll calculate the moles of strontium oxide used here. So for that we need to calculate the MR of strontium oxide, and that is equal to 87.6 and 16, right? So for that we get 103.6. So the atomic mass of strontium is 87.6 plus for oxygen is 16, and so it is 103.6. Now that's the MR, and so we can calculate the moles of strontium oxide, or you can also say the moles of strontium hydroxide is the mass, that is 0.333 divided by 103.6. Now that is equal to 3.214 into 10 power minus 3 moles. Now you can see the moles of strontium oxide is equal to the moles of strontium hydroxide because there is a 1:1 ratio. But if you compare within 1 mole of strontium hydroxide, the moles of hydroxide ions are twice, because here we have 2 in the formula. So 1 mole of the compound will give 2 moles of the hydroxide ions. So if we want to find out the moles of hydroxide ions, we need to multiply the moles of strontium hydroxide with 2. So if we multiply it by 2, we get it as 6.429 into 10 power minus 3 moles. Now these are the moles of strontium hydroxide. Now let's calculate the concentration of the strontium hydroxide, that is hydroxide ion. So we have moles divided by volume, and that is 6.429 into 10 power minus 3 divided by, now what's the volume? This whole number of moles are present in the total volume of 250 centimeter cube. So 250 into 10 power minus 3, now we are doing 10 power minus 3, that is divided by 1000 to change it into dm cube, and we get the answer as 0.0257. Now this is the concentration of hydroxide ions. Now if that's the concentration of hydroxide ions, from this we can directly calculate the POH. Now POH is minus log of the hydroxide ion concentration. So if we find out the direct minus log of 0.0257, we get it as 1.59. Now that is the POH. Now if we want to find out the pH, we have directly 14 minus POH that is 14 minus 1.59, which is equal to 12.41 pH. Or you can also do another formula, that is if we want to find out the concentration of H plus, we can do as Kw divided by the concentration of hydroxide. Now Kw, we know the value is 1 into 10 power minus 14. Now divide by the concentration which we have already calculated here, that is 6.429 into 10 power minus 3, and that's how you calculate the concentration of H plus and then pH. That also can be done. I find this as a better easier one, where we directly subtract it from 14 to calculate the pH. Now let's see what's next. I think the question 1 is completed here. Let's go ahead with question 2. Question 2a is when cobalt sulfate, that is COSO4, is dissolved in distilled water, a solution A is formed. So here is solution A, where cobalt sulfate is dissolved in distilled water. Now here is the whole series of reactions given. Let's see what is here on the first part. Complete table 2.1 to show the formula and color of each of the cobalt containing species present in A, B and C. Identify the type of reaction forming each of B and C. Now let's understand the formula of cobalt containing species, that is A, B and C. Now what is happening here? Solution A is present. Now how is solution A formed? We know that we have dissolved cobalt sulfate in water. When we dissolve that in water, we get an hydrated form of cobalt sulfate solution. Now what is the formula of the hydrated formula? Now cobalt containing species only we have to write, then understand it is just like copper. It forms cobalt H2O 6 times, and the overall charge of this complex will be 2 plus, because a ligand, that is H2O, is a neutral ligand with no charge. So the charge of the complex is equal to the charge of cobalt, which is 2 plus here. So this is the formula of the cobalt containing species. Now as we have dissolved that in water, this is the hydrated form of cobalt sulfate. So now if it is a hydrated form, the color of the cobalt hydrated is pink. So this is the pink color solution we will get. Now let's understand what is solid B. Now what is happening? We are adding sodium hydroxide to the solution and we get solid B. Now solid B means what? We have got precipitates of some compound. Now what are the precipitates? They are the precipitates of cobalt hydroxide. Now if you want to directly write cobalt hydroxide, that is also fine. But if you write the complex formula, then the complex is cobalt, where OH is written in twice form, and the remaining ligands, that is water, are 4. So total of 6 ligands are bonded to cobalt. Again here, if you count the charge, and it's going to be a neutral charge. Why? Because if there are 2 hydroxide ions, that will end up with -2 charge, and the cobalt have +2 charge. So overall charge is 0. So here no charge should be written. Now as it's a precipitate, so it changes to a blue color precipitate. So right here blue. Now these are certain things which you need to understand and learn. There is no other way out than just remembering the colors. Now if you talk about the type of reaction, as we have already seen, it's a solid compound B form. Now that are solid means precipitate, so you can call it as precipitation reaction. So the reaction type of reaction is precipitation reaction. Okay, now let's understand how is solid C. Solution C is formed. Now solution C is formed by adding excess of ammonia. Now here we have already got a species with this formula, And if you add excess of ammonia into this, then all the ligands are going to get replaced by ammonia, and that will be again 6 times. So let's understand the formula here. Again, if all the ligands gets substituted by ammonia, then again there will be 6 ammonia ligands bonded to the cobalt ion. And again the formula, that is the charge, will be 2 plus. Why? Again, because the ammonia is a neutral, that is uncharged ligand, so the charge of the complex corresponds to the charge of the metal ion. So 2 plus written here. And now color of the cobalt species is, you can say, yellow brown or brownish yellow, you can also write. And now, as I've already described you, that all the ligands are replaced, so you can call it as ligand exchange or ligand substitution reaction. Ligand exchange or ligand substitution, both is allowed. Substitution is also allowed, so you can write any one of it. Now the second part is, suggest a suitable reagent for the formation of cobalt chloride complex from the solution A. Now if we want again to form a cobalt chloride kind of complex, then understand we are going to replace all of the water molecule ligands from the cobalt complex from here, that is from the compound A or species A. Then we need to have a very concentrated solution containing chloride, and that is possible. And when we use concentrated HCl, concentrated hydrochloric acid is added, then only all the ligands of water molecule are replaced by the chloride ions, and we get the complex as COCl4 2 minus. Again the charge you can calculate, there are 4 chloride ions present, so they correspond to a -4 overall charge, and the cobalt have +2 charge, so overall it ends up with a -2 charge of the species. Let's understand B. Now the complex ion COCl4 2 minus has a tetrahedral geometry. Now the 3d orbitals in an isolated CO2 plus ions are degenerate. Now what do you mean by degenerate? Degenerate means all the orbitals of D, that is 5d orbitals we have, they have same energy, so we call it as degenerate. And the complete the figure 2.2 to show the relative energies of 3d orbitals in an isolated CO2 plus, that is cobalt ion, and in the cobalt ion of a tetrahedral complex which is formed here. So if we talk about the degenerate first, which is present in an isolated CO2 plus ion, isolated we know is without the ligand. So here 1 2 3 4 and 5 d orbitals I am drawing here, and they're all degenerate, that is they are at the same level, same energy. Now when bonds with the ligands of chloride, it splits into tetrahedral complex. Now there are 5 d orbitals that splits into non-degenerate. Non-degenerate means it splits into 2 different level of energies which is different. And for tetrahedral it is 3 orbitals on the top and 2 orbitals at the bottom level. But for octahedral it will be opposite, that is 2 on the top and 3 at the bottom. So here if we split them, then 2 will be lower, that is we'll draw it here, and 3 on the top with the higher energy level. Now why does this happen? This happens because the ligands which we have added here, they are all negatively charged and they will repel each other, and so now the d orbitals split into 2 different levels, and so we draw it like this here. That is, in the tetrahedral complex with the chloroligands, it will split into 2 different energy levels. Now the second part is draw a 3-dimensional diagram to show the structure of the complex, that is COCl4 2 minus, and we have already know that it is tetrahedral. Now if we want to draw tetrahedral, this is how you draw, but if it is 3D, then you need to draw a bold line and a dotted line. Here all the chloro ligands are bonded, so we'll draw it chloro. And we know that the structure have an overall charge of 2 minus, so we can draw it as 2 minus like this. Now let's see what's the sub question. C is H2O2, that is hydrogen peroxide, can act as an oxidizing agent or a reducing agent when reacting with species that contains manganese. So manganese metal we are talking about, and here table 2.2 shows electrode potentials for some electrode reactions, and it's given all here. You can see there are two hydrogen peroxide equations given with the acidified and the alkaline conditions, and the electrode potential value is also given, and then along with that we have a third hydrogen peroxide equation given here, but here it is the reverse one. Now let's see what is the question all about. Here it talks about the compound, the species containing manganese, and here we have two more half equation which contains manganese as one of the species. So let's see what are the sub questions. Use only the species listed in table 2.2 to suggest one reaction in which hydrogen peroxide acts as an oxidizing agent. Now let's talk about oxidizing agent hydrogen peroxide again, and the one reaction in which hydrogen peroxide acts as a reducing agent. So we have to use hydrogen peroxide in both ways. Include the values of the standard cell potential, that is E cell, and an overall equation for each reaction. Now so we have to find out an species in which hydrogen peroxide is acting as an oxidizing agent. Now what I teach my students is that we have to write equations in such a way that we have one equation, equation 1, where the E cell value is greater on the top, so a higher value on the top. Another equation 2 where the electrode potential value which has a lower value, and it has to be written at the bottom. And if it's an equation, we'll obviously have right hand side, left hand side species. I always say that this species in the equation 1 on the right hand side is going to oxidize the species on the second equation on left hand side. So this is how we are going to understand here. Left hand side and right hand side I reversed. So species on the left side is going to oxidize the species on the right side of the second equation. Correct? I hope the things are clear. Let me repeat that the species on the left side of equation 1 is going to oxidize the species on right hand side of equation 2. And how do we get equation 1 and 2? The one with the higher electrode potential value has to be written on the top, and the one where the electrode potential value is lower has to be the second one. Now, so if we are talking about hydrogen peroxide oxidizing agent, then we have to choose hydrogen peroxide equation in such a way that its value is higher than the species of manganese. Now if you compare these two, it is plus 1.78 and plus 0.88, and we have another two manganese species where it should have a lower value, then only it can oxidize, the hydrogen peroxide can oxidize the manganese. Now here we can see that both the manganese species are on right hand side, and both these values have a lower value compared to 1.78. Now we can't use 0.88 with this because that has a higher value. So I prefer that we can use this one with any of these two species. In this, hydrogen peroxide is definitely going to act as an oxidizing agent. I hope my explanation of equation 1 and 2 is very clear. So now if we check, hydrogen peroxide is going to act as an oxidizing agent for which manganese species? So if I take this one, the second equation here, then it's going to oxidize the Mn2 plus manganese ion. Why? Because I said the species on the right side will be oxidized. So Mn2 plus will get oxidized with the hydrogen peroxide here. So I should write it X as an oxidizing agent for Mn2 plus. I can write that. Yes. Now how do we calculate the E cell value and how do we make an overall equation? Now, the first thing we need to understand is that the one which is lower in the electrode potential value has to be reversed, because if manganese Mn2 plus is going to get oxidized, is going to lose the electrons, so electrons has to be on the right side. So if I add both the species, both the equations and write, then first I'm going to write hydrogen peroxide plus 2H plus. I'm just going to show you the whole workout, but actually you don't need to show the whole workout. You can just write the main equation. So this is the hydrogen peroxide reaction, and if I reverse the manganese ion equation, then it's going to be this way: 2H2O and also MnO2 plus 4H plus 2 electron. Now if we add on both the equations, then the electrons will get cancelled on both sides. The water molecules also get cancelled because both of it are 2 electrons each, 2 water molecules each. Now if we just add on, then we get H2O2 plus Mn2 plus 2H plus, that gives MnO2 plus 4H plus, right? This is the equation. You will get overall equation. Okay, now let me correct here also. Then here we have 2H plus and 4H plus. If we subtract these two, we'll be left with only 2H plus on the right hand side. So we don't need to include 2H plus and 4H plus. We just have to write 2H plus on right hand side. Now how are we going to calculate? So this is the only equation you need to write in your answer. You don't have to write the workout, you don't have to show the workout. This you can do in some rough page or blank page there, and you can work out, because here it's going to occupy more space which is not given to us. Now we also have to calculate the E cell value of this. Now simple E cell value I'll calculate here is, we just have to subtract two values, and the two values here we have is 1.78 and 1.22. 1.78 and 1.22. If we subtract directly the two values, we get plus 0.56 volt. So don't forget writing the unit. Here I have written, because as you see we have less space. I will show you in the whole working. So you can write these two equations in the blank page and work out. You will get enough space. So work out you will have to show, and you will get space for it. Now hydrogen peroxide acting as a reducing agent. So here it applies the same. So if we have a look at the same thing, you need to choose a species now equation where hydrogen peroxide have a smaller value, then only it will act as an reducing agent. Why? Because it goes reverse. If the species here in the equation 1 is going to oxidize the species of the second equation on right hand side, then it goes reverse, that the second species on the right hand side of second equation is going to reduce the species of equation 1 on left hand side. It goes reverse. So this has to be reducing agent. Now so if we want hydrogen peroxide as a reducing agent, then it has to be in the second equation with a lower electrode potential value. So in that case, if we choose, this is the equation for hydrogen peroxide, where it has got the lowest value and the hydrogen peroxide is on right hand side of the equation. Now if you need to choose a manganese species who have a higher electrode potential value than 0.68, and that is possible here only in this case because this value is negative. So only these two species, these two equations here is possible, that is equation 2, and the last one, that is fifth equation. So this we have to take for our calculation, as I've shown you here, equation 1 and equation 2. So choose this as equation 1 and equation 2 here with a lower electrode potential value. So hydrogen peroxide acts as a reducing agent with MnO2, that is manganese 4 oxide. So, yeah, so here we have to write that answer, acts as a reducing agent for MnO2, right? Now if we work out in the same way the equations which is given here, let me write the equations here for hydrogen peroxide at the bottom. Hydrogen peroxide here with O2 plus 2H plus 2 electron. Yeah, this is the lower equation. And for the equation of MnO2 here, it is MnO2 plus 4H plus 2 electron gives Mn 2 plus 2H2O, right? So these are the two equations we have chosen. Now if we work out, sorry, I forgot, you have to reverse this. So let me reverse it. Yeah, so now let me reverse it here. I'm reversing the fifth equation given here. I hope that's very clear. So H2O2, that gives O2 plus 2H plus 2 electrons. So now we can cancel out the 2 electrons, we can cancel out the hydrogen ions with 2H plus remaining here and just add on, right? So our overall equation is going to be MnO2 plus hydrogen peroxide plus 2H plus, that is 2 hydrogen ions with Mn2 plus left over and oxygen also, and the 2 water molecules, that is 2H2O, which is present here, O2 and Mn2 plus on the right side, and on the left side MnO2, hydrogen peroxide, and then 2 hydrogen ions. So this is how you're going to make the overall equation. And if we calculate the E cell value, again we'll have to just subtract the two values, and what are the two values given here is 1.22 and 0.68. So here 1.22 minus 0.68, that gives us plus 0.54 volt. So this is how you're going to work out. I hope my explanation is clear because the space given is gone too small, but I have shown you the whole working. Yeah, so this is how you're going to solve this question. Let's go ahead with the D part. Here D is acidified manganate ions MnO4 minus can be used to analyze the content of iron tablet by titration. Now 2 identical iron tablets are crushed and dissolved in distilled water. The resulting solution is made up to 150 centimeter cube with distilled water. Understand, the total volume is 150 centimeter cube for what? The iron tablets. 25 centimeter cube of this solution requires 18.60 centimeter cube of 0.0500 mole per dm cube of manganate solution to reach the end point. All the Fe2 plus ions are oxidized, and here are the two equations given. Now describe the color change observed at the end point of this titration. Now understand, what have we taken in our volumetric flask was the iron tablet. So we have taken Fe2 plus, and that we are reacting with the MnO4, that is manganate ions. So obviously initially the Fe2 plus solution is colorless, and when we keep on titrating it with manganate ions, the end point will be pale pink or light pink color, which will be permanent color. We don't have to allow during the titration to go the pink color very dark. It has to be very light pink color. So we will specify it as light pink color. Now here it's given, calculate the mass in milligram of iron in 1 tablet. Assume that all the iron in the tablets is Fe2 plus only and show your working. Now if we start with, what do we have to find out? We have to find out the mass of Fe2 plus in milligrams in 1 tablet. Now understand 1 tablet. Why? Because we have used 2 tablets to make the solution. So okay, starting with what we have got is, we have got the volume and concentration of manganate ions, that is, so we can calculate the moles of manganate ions, MnO4 minus, that is concentration into volume. So if we substitute the value, we have concentration as 0.0500 multiplied by the volume, that is 18.60. Now that will divide by 1000 because we need to convert the volume centimeter cube into dm cube, and so our moles of manganate ions, we end up with 9.30 into 10 power minus 3 moles. Now here are the two equations given for the manganate ions, and if these two species are reacting, we have to balance the electrons, so multiply that by 5. So here we get 5 and then just add up. So that 5 electrons gets cancelled up. If you add up, we have already seen how to make an overall equation. So in that case, the ratio of manganate to Fe2 plus is 1:5 ratio. So in that case, the moles of Fe2 plus is going to be the 5 times. So 9.30 into 10 power minus 3 multiplied by 5 has to be done to get the moles of Fe2 plus. So if we multiply this, we get 4.65 into 10 power minus 3 moles. Yes, these are the moles of Fe2 plus, but then understand this is just the titration value, and that titration value is just for 25 centimeter cube of the iron tablet solution, because we have calculated it with the help of titration. But if we want to find out the total moles of Fe2 plus in how much volume, we have made volume 150 centimeter cube. So if we want to find out the moles of Fe2 plus in 150 centimeter cube, then we need to multiply this value 4.65 into 10 power minus 3 with 6, because 25, if we have this much, then for 150 centimeter cube, how much? You can cross multiply also, so you can even multiply 150 divide by 25, that also can be done. In place of multiply by 6, you can have multiply by 150 divide by 25, that also can be done cross multiplication, but I have done directly multiply by 6, and if we multiply, we get the value as 2.79 into 10 power minus 2 moles. So these are the moles of total moles of Fe2 plus in the total solution which we have made. Now from this we can calculate the mass. Mass is equal to moles into the mR, that is atomic mass of iron. Now we have already got the moles, total moles, that is 2.79 into 10 power minus 2. You can check the periodic table to find out the atomic mass of Fe iron, that is 55.8. So on multiplying this, we get as 1.557 grams. Now this is the mass of Fe in grams also, and also it is the mass of 2 tablets. So if we want to find out the mass of Fe in one tablet, then we need to divide this 1.557 by 2, and so we get the answer as 0.778 grams. Now if this is 0.7785 grams, right? So if we want to find this is in milligrams, we need to multiply that by 1000, and so we get the answer as 778.5 milligram. We have just converted grams into milligrams by multiplying it by 1000. So, and so we get the answer as 778.5 milligram. I hope you understood the whole explanation. We started with the titration, that is the moles of manganate ions. From that we calculated the moles of Fe2 plus, which was oxidized through this equation where the ratio was 1:5. Now this were the moles in 25 centimeter cube. So from there on cross multiplication we got the moles of Fe in 1 centimeter cube, in 150 centimeter cube, and from that we found out the mass, that is moles into the atomic mass of Fe. Now that was the mass of 2 tablets given in the solution. So we found out the mass of tablet in 1 by dividing it by 2 and then changing it to milligram. So this is how we got the answer. I hope the whole process is very clear. The explanation is also very clear. So here is question 3. Now here the first A part is define entropy. Now what is entropy? In one word it can be also defined as the disorder of a system, or randomness of a system. But if we define it in a specific way, then we also can write as it is the different types or different possible arrangements of molecules and its energy. Also you can write molecules and its energy in a given system. Now most of the time given system means it can be either a solid, liquid or a gas, or you can also consider it as a reaction in which one of the species is changing to other species. That is also possible. So define entropy, but in a reaction, then in that case we'll be finding out the change in the entropy. So let's see what's the sub question B says. Here a diagram is given. Figure 3.1 shows how entropy S, here is entropy S, of a pure substance changes with temperature T, and here is the temperature on y-axis, x-axis, and entropy on y-axis. Now here it's written, identify the process occurring at each of the temperatures T1 and T2. Now understand the temperature is increasing, and so the entropy is also increasing, because as temperature increases, entropy increases, that is the randomness of the system increases. Now at one particular point the temperature remains constant, but the entropy increases all of a sudden at the same temperature. Now what is that temperature? T1. So obviously this temperature T1 should be the melting point. So what is the process which is occurring here? They have asked the process. So process is the melting which is occurring here. And if you talk about the temperature T2, same thing is happening here. At T2 the entropy increases all of a sudden, but the temperature T2 remains constant for some time. Now that has to be the boiling or the evaporation which has to occur at T2. So here are the processes which occurs at T1 and T2. The sub question 2 is explain why the entropy change delta S at T2 is bigger than the entropy change at T1. Now let's understand what is being asked. Here you can say that the entropy change at T1 is given by this change. So this is the change which is happening at the melting point. But if you compare the entropy change at temperature T2, this delta S, the entropy change, is quite bigger than the entropy change happening during melting point. Now let's understand the change in the entropy at different state. Now understand the entropy in solid will be the least, right? This entropy in the liquid state of the same substance will be greater than in the solid form, and the gas form of the same substance will have the highest entropy because the molecules are very far apart, they are randomly arranged, and so there are different ways of arranging these molecules of a pure substance in gaseous state, and so the entropy is also very high. So that's how we are going to explain here, is that the change in the entropy, occurring when liquid changes to gas is higher than the entropy change, which occurs when a solid changes to liquid. Why? Because the gases have the highest entropy, and that's why the boiling entropy will be, change in entropy will be much higher. So here is again sub-question C given here. The sub-question C is the equation of the reduction of iron 3 oxide by carbon monoxide at 450 degrees Celsius is shown here, and here is the equation. Delta G, that is Gibbs free value, change in the Gibbs free value, is also given here, that is minus 36.2 kilojoules per mole. The table 3.1 shows the enthalpy of formation and entropy for some substances given in the equation. Use the data in table 3.1 to calculate the entropy of a carbon monoxide at 450 degrees Celsius. So here we are supposed to calculate the entropy of carbon monoxide, which is missing here. The other values are given. Okay, so what is the equation, which formula which relates delta G, enthalpy change, and entropy? That is delta G is equal to delta H, standard form obviously, minus T delta S. Now here we have Gibbs free energy, the enthalpy change, and temperature, and delta S. But then for that we'll have to calculate delta H, that is enthalpy change of the system first. And so for that we'll have to subtract the product values minus the reactant value. So what are the product values here? Fe is given, which has 0 value for enthalpy of formation, and carbon dioxide is given. Now carbon dioxide are 3 molecules, so multiply that by 3. So 3 into minus 393.5, that is the product value, minus the reactant values. So here Fe2O3 is 1 only, so minus 824.2, plus the another reactant, that is 3 carbon monoxide, 3, so multiply the value by 3, so plus 3 into minus 110.5. So this is the enthalpy change we'll calculate, and the answer is minus 24.8 kilojoules per mole. Remember, the values are given in kilojoules per mole, so our enthalpy change will also be the same. Now if we substitute these values into the equation and rearrange the whole equation to get the entropy change, then we get as entropy change is equal to delta H minus delta G all in standard form upon the temperature. So if we substitute all the values, enthalpy change is minus 24.8 minus of the Gibbs free energy which is given in the equation, that is minus 36.2. So this is the numerator value, divide by the temperature, that is 450 degrees Celsius. Here we have to add 273 to get the temperature in Kelvin, which is 723 Kelvin. So divide by 723 Kelvin. So if we substitute all of these values, we get the entropy change as 0.01576. That is, now answer is in kilojoules, but we don't want kilojoules because the entropy change given here is in joules per Kelvin per mole. So if we want to change this kilojoules into joules, we need to multiply it by 1000, and so we get the value as 15.8. That's what we can write in three significant figures. Now let's calculate the entropy of carbon monoxide from this. Now entropy of all these are given, so total entropy change again is product minus reactant. So in that case, if we find out the value, okay, carbon dioxide value has to be multiplied by 3, the Fe value has to be multiplied by 2, and Fe2O3 is one molecule, so we have to use as such. Now substituting all these values, then if we write it as the product side first, 2 into 27.3 plus 3 into 213.8. This is the reactant side, product side minus the reactant side, that is 87.4, one molecule, plus the value of carbon monoxide, but we know the value of carbon monoxide has to be multiplied by 3. So if we take that value as 3x, yes, 3x, then this is how we work out, and we have already got this value as 15.8 joules per Kelvin per mole. So if we work out the value for 3x, then we get as 15.8 into positive 608.6 minus 3x. Right? So if we work out again, then we get the value of x as 197.6 joules per Kelvin per mole. So let's write 197.6 here for the carbon monoxide value. I hope the whole explanation and the equation is very clear. The entropy change has to be calculated for product entropy minus the reactant entropy. And if we do that, the multiplication of the molecules also has to be considered, the number of molecules. So here carbon monoxide value is multiplied by 3 to keep it as 3x. And so this is how we get the value. Let's go ahead with the D part here. Okay, here is the question D. Iron 2 oxide can also be reduced to iron by carbon monoxide as shown. Here is the equation given, and the enthalpy change and the entropy change values are given. Now state the effect of increasing the temperature on the feasibility of this reaction. Let's understand what is all happening. So first let's calculate the delta G value to understand whole, that is delta G is equal to delta H minus T delta S. And if we substitute all the values, understand this is joules value, so we'll have to divide it by 1000 to change it into kilojoules. And so if we substitute all values, we have minus 11.1 minus the temperature we are keeping as T only, and that is the delta S value as minus 15.2 into 10 power minus 3 I'm writing here, and this is the whole equation we get. We can summarize that as minus 11.1 minus T delta S. Now the point is that if we want to have delta G negative, then only the reaction is feasible. Understand, delta G is negative, then only the reaction is feasible. Now if we want delta G to be negative, then what happens to the second term here is that the negative and negative value of delta S makes the second term positive. Now if the temperature increases, then the second term becomes a more higher value, then the delta G tends to be positive. Got it? The second term is positive because the negative and the negative delta S makes it positive. So if the temperature increases, the second term tends to be a higher positive value, making delta G also positive. So that shows that increase in the temperature may decrease the feasibility of the reaction. And so that's what we are going to explain, is that increase in temperature will decrease the feasibility, of reaction as delta G gets less negative or more positive. That is how you can explain less negative or more positive, and that's why the feasibility decreases. Understand, delta G is negative, then only the reaction is feasible, right? So I hope the explanation is very clear. Here we ends with question 3, and the question 4 we are going to discuss in the next video.